In the previous few slides, we have already reviewed on how we evaluate the equivalent transfer function of a feedback system. But this kind of feedback system might not be the most complex system that you might have. You might have much more complex than just a feedback system. In order to analyze the complex block diagram that involves a lot of subsystems, let's say more than the number of subsystems that you might have in a feedback system, we need to have a reduction of the block diagram. We need to reduce the complexity of the block diagram with some techniques to analyze the equivalent of the transfer function. The block diagrams in a complex form, you might have a complicated block diagram. It might involve some subsystems with different transfer function. It might also involve some branch points, summing points, and in order to simplify this block diagram, to reduce the complexity of the block diagram, we need sometimes to interchange the summing point, the branch point, and many more. So I will share you some, let's say, tips and tricks to reduce the complexity of block diagram to analyze the transfer function of the complex block diagram. Okay, in this slide, you can see the example of a complex block diagram. This might not be the most complex block diagram that you might encounter again, but this will illustrate on how complex the block diagram you might encounter. So if you look at this complex block diagram comprises 4 subsystems with different transfer functions. So you have one block with a transfer function of G1, G2, H1, and H2. And if you look at the flow of this block diagram, there are some branches like the one that I indicate here. You have 2 branches, and there are also some summing point. At least in here you have 3 summing point that you can see here. Okay, this causes the complexity in the block diagram. For instance, if you look at this, there is one flow coming in here, but there is also another flow coming into the first feedback. So this causes some confusion, this causes some complexity when you analyze it, because we have a tangled system here. One is moving to the left, the other one is moving to the right inside the previous loop. So we need to simplify this block diagram. To be honest, there is no straightforward way to simplify the complex block diagram. We need to do some trial and errors. We need to be familiar on how to simplify the block diagrams. What I can share with you in the next few slides is only some tips and tricks that we normally use to simplify block diagram. At least there are 5 tricks that I can share with you starting from the following slide. So okay, in this slide you can see the first trick that I want to share with you. You might have a complex block diagram in which you will simplify it only if you can swap a transfer function in one of the subsystem of the block diagram with the summing point that follows that transfer function G. So in this case, I have a transfer function G followed by a summing point. And in our complex block diagram, this causes a high complexity in your block diagram to analyze. And you need to swap these two, because by swapping it, you will simplify the block diagram. If you want to swap this, you can swap it easily. But if you swap it, so in this illustration, in this slide, I will put this summing point before the block G. if I put the summing point before the block G, it will become this one. So the summing point now appears before the block G. You can swap it like that, but if you do that, you have to add one more transfer function before the summing point, where the transfer function is equal to the inverse of the block G. Okay, so these two subsystems basically are equivalent. These two are the same, which means, of course, you can change this subsystem with this subsystem if you need to simplify your block diagram. How to show that these two are identical? If you want to show it, you have to make sure that the output of these two subsystems are identical. So if we analyze it, if you refer to the first subsystem, we have an input A that is coming to the block G. So the output of this block G at this point will be A times G. And then after that, we meet the summing point. This summing point will subtract the AG with B. So the output of this summing point will be A times G minus B. If the subsystem on the right side has the same output, then you can show that these two subsystems are identical. So let's try it then. If we look at this part, there is an input B coming to the transfer function 1 over G. That means at this point, the value will be B times 1 over G. And then after that, we meet the summing point. The summing point will subtract A, the first input, to the second input. So I will subtract A by B over G. And this will be the output of the summing point. So at this point, the value will be A minus B over G. And now this value, A minus B over G, is the input to this transfer function, to the transfer function G. Which means the output of this block, the output of the block G, will be equal to the transfer function G times the input A minus B over G. Right? If you multiply it, then this will be equal to A G minus B, which is equal to the output of the first subsystem. So by showing that the two outputs are identical, you can show that these two subsystems are identical. Okay. So to illustrate it again, after the first summing point, the output will be A minus B times 1 over G, which is at this point. And this will behave as an input to the block G. So the output of block G will be this input times G, which is equal to AG minus B. This is exactly the same like the output of the first subsystem. So in here we show that these two subsystems are identical. In this slide, I will share you the second trick. There might be a case where you have a complex block diagram. It looks complex in a sense that your block diagram looks tangled. There are a lot of branches coming here and there are a lot of summing point. Everything looks tangled. And then you feel that you will be able to simplify the block diagram by swapping two summing points, two consecutive summing points. If you want to swap two consecutive summing points, you can do it easily. So for instance, in here, in the left subsystem, you have the first summing point here that will add the first input A with the second input B. So at this point, the value will be A plus B. And then the second summing point will subtract the first input A plus B with the third input, C. So the output will be A plus B minus C. Okay. Now I want to swap these two summing point, because probably now in my case I can simplify a complex block diagram by swapping these two summing point. If you want to swap these two summing point, you can swap it easily. You don't have to add anything else on it. So this is the second summing point in the subsystem on the right side is the second summing point. Now I put the second summing point before the first summing point. Okay, so if you analyze this subsystem on the right side, the output at this point, the output of the first summing point will be equal to A minus C. And then the output of the next summing point will be A minus C plus B. These two are also identical. So in short, if you have two consecutive summing points, you can swap it easily without any changes on the subsystem. The third trick that I want to share with you, you might have a case again where you have a block with a transfer function of G, and then there is another branch point following that transfer function G. There might be a case that this arrangement cause complexity in your block diagram. You need to simplify it by swapping these two. So you want to put the branch point before the block diagram G. You can do that. But if you do that, so if you put the branch point before the block G like this, you can do that, but you need to add one block on the second branch. These two are also identical. So again, there might be a case when you need to simplify your complex block diagram by swapping a block, one block with a transfer function G, let's say, with the branch point that follows the G. You can do that. But if you do that, you have to add another block on the second branch. The fourth one, the fourth trick that I need to share with you is like the opposite of the previous trick. So in this case, you have a branch point that comes before the transfer function G, and then you want to swap it. It's similar to the previous one, but in the opposite manner. You want to put the branch point after the transfer function G. If you want to do that, yes, again, you can. So on the right side, I put the block G, I put the transfer function G before the branch point here. But if you do that, you need to add one more transfer function on the second branch with a transfer function equal to the inverse of the block G. So you need to put a transfer function 1 over G on the second branch. These two again are identical. This might help in simplifying your complex block diagram. Okay, so this is the last trick that I want to share with you. Let's call it trick number 5. We might have a subsystem from our complex block diagram that looks like a feedback system. The one that we discussed in the previous few slides in the previous subtopic. So this exactly looks like a feedback system where G1 is our forward loop transfer function, and G1 times G2 is our open loop transfer function. This subsystem, the subsystem that looks like a feedback system, we can replace it with a single block where the equivalent transfer function can be evaluated with the equivalent transfer function of the closed loop system. You still remember the equivalent transfer function of a feedback system will be equal to forward loop transfer function. divided by 1 plus open loop transfer function. It is positive in here because we have negative feedback in here. Okay, so this will be equal to the forward loop transfer function is G1, the open loop transfer function is G1, G2. So I can replace this subsystem that you might have in your complex block diagram with this one single block. In addition, I want to share also to you that this feedback system is also equivalent to this system. It might be a less likely case that you might encounter here when you want to replace this feedback system with this another feedback system like this. But I just want to share with you that these two are also equivalent. But the most important thing is you can replace this feedback system with one single block like this. Okay. Okay, so those are the 5 tricks that I shared with you. Using these 5 tricks, if you stick to these 5 tricks, you should be able to simplify any complex block diagram. Again, as I mentioned before, I don't have a straightforward answer on how to do that, but you just have to do some trial and errors using all of these 5 tricks, and you will be able to simplify a complex block diagram. In this slide, I will give you some one example on simplifying a complex block diagram. So if you look at this again, I have already popped up this slide before. This complex block diagram comprises 4 subsystems: G1, G2, H1, and H2. We are going to analyze it. We are going to simplify it. We want to find the equivalent transfer function of this complex block diagram. But this one is not really straightforward to solve it because there are some branches, there are some summing point. One of the branch is moving to another loop like this. It's not easy to solve it. So how are we going to solve it? We have to use the 5 tricks that I shared with you in the previous slides to simplify this complex block diagram. Let's do it one by one now. I will start it by using the second tricks that I shared with you before, the swapping of 2 consecutive summing points. So if we look at this block diagram, there are 2 consecutive summing points where if we swap it, we can simplify, we can solve the tangled problem here. So if you look at this, there is a kind of a tangled problem. There is one loop coming in, but then there is also another loop coming inside the first loop. So we don't like it. This causes tangled in our block diagram here. So if I can untangle this, I should have a simpler block diagram. So what I'm going to do, I will swap these 2 summing points. The 2 summing points where I indicated with a red color here. Somehow, intuitively, of course, if I swap this, I will untangle the problem here. So this is the first step that I'm going to do. I will swap these 2 consecutive summing points. See, after we swap it, somehow our complex block diagram looks somehow simpler in a sense. We have 2 separate loops. Okay, and then what next? Next, I will simplify this problem. If you look at this part, there are two transfer function h1 and h2, where basically these two transfer functions are combined by the third summing point here. So I can simplify this part, the one that I circled with a red color here. I can simplify it by just summing these two blocks. But be careful in here, I have a summing point with a positive and negative sign. So if I want to simplify this part, I can just sum these two, h1 with negative h2. Again, if you look at this point now, somehow my complex block diagram looks simpler. And then what next? Next, you have the two branches. This branch, the first branch, is coming through block G1, and then I have to sum it with the second branch, where the second branch there is no transfer function on it. What does it mean? This means we have a unity transfer function, so you can consider this with a transfer function equal to 1. It's unity transfer function. So I can simplify this part. If I consider the second branch contains a block with a unity transfer function, I can redraw it into something like that. And then looking at this summing point, I have to sum these two transfer function. Okay, so I can replace this part, this subsystem, into something like this: 1 plus Q1. If you look at the right side, what do you see here? This part looks like a feedback system, where the G2 is the forward loop transfer function, and G2 times H1 minus H2, G2 times H1 minus H2 is the open loop transfer function. So using the formula that we discussed in the previous subtopic, where the equivalent transfer function of this subsystem will be equal to forward loop transfer function divided by 1 plus open loop transfer function. Again, why is it positive? It's because we have a negative sign here. We can replace this subsystem with one single block. Okay. At the end, what do we have? We have two systems, two transfer function in serial connection. So it is a cascaded block basically. So you can replace these two transfer function in series by just simply multiplies these two transfer function. Okay. So as a result, this is the equivalent transfer function of our complex system. Okay, as a summary on this session, we have already defined different types of mathematical model required for a dynamic systems. We have already discussed how to translate different types of mathematical model. And the last part, we have also discussed on how to derive a transfer function from a block diagram model. Thank you for your attention, and see you again in the next session.